Thank you, Umberto. Let me remind you that yesterday we defined this. So we worked on this space omega, which was the space of paths smooth paths in symplectic manifold with x0 and x1 belonging to Lagrangians. So this was my version of relative Floer homology, and we wanted to do more theory on this space. So we defined a functional whose critical points were exactly the paths which satisfied phi t of xt equal to phi t of x0, which means that they are Hamiltonian chords between the Lagrangian and itself. And by this correspondence, gamma, they were in one-to-one correspondence with the intersection between L and phi 1 minus 1 of L. So this critical point corresponds somehow to a Lagrangian intersection. And then we wanted to do more theory. So in order to do more theory, we defined this Morse complex. So the Morse complex was defined by the following. So this was the Z2 free vector space spanned by the critical points of AH with this Maslov index equal to K. Right? And then we wanted to define a differential dk CFK fk minus 1. And in order to define this differential, we took a gradient for some metric. And actually, the gradient equation for this metric is the following, is the Floer equation. Meaning that the gradient trajectories are just half cylinders with boundary on L, right? And now we want to go further with the construction and define this differential. In order to define this differential, what we have to do is to consider for x and y critical points of AH, consider this space MXY, the space of solutions. So U solution of 1 such that the limit on S minus infinity of U is X, limit on S plus infinity of U is Y. So let me emphasize that R, of course, R acts on M because if U is a solution, then just translating by a real parameter, we still got a solution. This U still satisfies this equation. So then we can define Lxy is mxy divided by R, just in analogy with what happens in Moore theory, right? And as in Moore theory, it's easy to see that if you just take a solution and write this expression. So what you get here is dA of du ds, which is actually dA of minus gradient A, and this is negative, except in the critical points. So actually, if x is different from y, then this expression, the function is strictly decreasing on this trajectory, which is the case in Moore theory also, right? And in particular, R acts freely on M. Okay, so yeah, I mean, like in Moore theory, well, it's more easy to see it. In Moore theory, you can visualize this space Lxy by intersecting the points of your solution with some intermediate level, which is very geometric in Moore theories. We can do it here also, but of course you do not have this geometrical image. Now, the definition is, of course, now the definition of delta x is the following. You just take nxy y, and this your sum goes through critical points of Maslow's index, one less than the one of x, and nxy is the number modulo 2 of this solution space Lxy. This is what one does in Moore theory. Now, of course, there are many problems to solve here, because one should say why this is finite and why delta square is 0. So we come here to this general plan I gave yesterday in order to have these properties. And the general plan was composed by 3 steps. So let me go to, I think this is 4, the 3 steps: transversality, gluing, compactness, and gluing. And let me start with transversality. So what do we want? We want to have M, X, Y, MXY differential manifold of dimension mu x minus mu y, so that Lxy will be of dimension less, 1 less. And this is what we want, because we want to Lxy to be a manifold of 0 dimension. We want it to be a compact manifold of 0 dimension in order to have it finite, in order to define this number. Okay. So how to prove that? Now let me, if you want to prove that something is a manifold. So in finite dimension, what you do, a method to get a manifold is the following. So if you have some f, say, in finite dimension, so m to some p, and here you have some manifold, then f minus n is a submanifold of m if f is transverse to n. Transverse to n, meaning that you have here, so tx f txm plus tfxn is tfxp. So this is the meaning of transverse. I think everybody knows. Now, if you have a particular case here, where here P is some total space of a vector bundle, B. And so N here is the zero section, right? Now, so still you have this application, F, M in E. What you have to do then to check this, transversality property. So this is the zero section, and this is E, and this is the fiber here, EFX, and here you have the image of TXF, and you want to have this image transverse to this 0B. So what you have to prove then is that this projection here is surjective. So have to prove that this projection on the fiber Fx of the image TXF is surjective. Now this will be our case. Here. Now let me give you the relevant spaces. So first of all, the role of M will let me denote it by C infinity xy. These are just so I will denote it like this, meaning there are smooth half cylinders with boundary in L, right, and limits in minus infinity of u is x, and in plus infinity is of u is y. So this is the space, and this is the space B also. Okay, and E will be C infinity of R 0, 1 T TW such that the projection, such that the projection on V of some element like this, so say, how to denote it, W, such that the projection on V of W belongs to this space. So this means that what we have here, the fiber is just formed by smooth vector fields tangent to W along U. So with this notation, we have this Floer operator F, which can be seen as going from B to E. F U is du ds plus j du dt plus gradient h of u, and it can be seen as a section of this vector bundle, right? And saying that u is in M xy is the same thing as saying that f of u belongs to this zero section. Zero section. Right? I wrote it like B, but it should be zero. Well, I don't know. Zero B, zero E. The zero section, in any case. Okay? So I have then to solve this transversality problem, namely to prove that, so I want to have this, according to what I wrote here, I want to have the projection on the fiber composed to the differential of this operator surjective for any u which is solution of the Floer equation. Okay? So yeah, so if I have it, it's good. If I do not have it, what I want to do is to fix J, with which is the almost complex structure, and then perturb H to have this property. Okay? And so to have this manifold structure. Now, I have a naive plan to do that. Let me show you my plan. So first, I take U about a neighborhood. So let me fix first. Denote this by H0. H0 to be perturbed. Okay. So take U a neighborhood of H0 in C infinity R times 0, 1, no, W times 0, 1, R. Actually I will write it like this. H in C infinity W times 0, 1 R, and I want this perturbation to be equal to H0 near the critical points of AH0. So say H equal to H0 near the critical point of H0. And actually, I want to be this neighborhood small enough so that actually any H here, for any H here, the critical points are the same. I do not want to perturb in order to change the critical points of the function. So I perturb far from the critical points. Okay? So this is kind of a say, call it space of perturbation. And then I define this, so say, theorem, but this is what I want to prove, that this space, which is formed by H and U belonging to this U times C infinity xy, such that the Floer equation, so these are solutions of the Floer equation for this Hamiltonian, right? So I want to prove that this is an infinite dimensional manifold. So actually one can see this as the following thing. So you have to define gamma on so u times c infinity xy gamma of h, and u is du ds plus j du dt plus gradient h u. And this z is gamma minus 1 of this, again, of this zero section, right? So in order to have this, you need to have this surjection property. So you need to have this projection for any h u in gamma minus 1 of 0b. You need to have this projection, as I said before, projection on the fiber composed with the differential of gamma to be surjective. Okay, actually I can, if you write this LU, you can write this too. So this is on h y. This acts like this differential acts like L u y plus gradient u of h. So what I did is actually I added the spaces of parameters in the source of my function, which I wanted to be a submersion. So with this procedure, I hope to have much more chances to have this function as a submersion, and therefore to define the manifold. Of course, it won't be the manifold I wanted to. It would be it will be a great manifold of infinite dimension. Okay. So this is the first part of my plan. The second part is the following. So just once this manifold defined, take the projection on U, the usual obvious projection, which is this one. Okay. And then apply a Sard theorem. Sard theorem tells you that the set of regular values of pi is open and dense. So you pick a regular value, and you pick a regular value if h is a regular value. Then you have pi minus 1 of h is a submanifold, and actually pi minus 1 of h is exactly this this space, right? So this was the plan, but this plan does not work because this Sard theorem I stated there is not valid in infinite dimension. So in infinite dimension, the relevant statement is called Sard-Smale, and Sard-Smale is the following. So if let J E and F have to be Banach manifolds, and J from E to F such that D U G is Fredholm for any U, then the set of regular values of G is open and dense. Okay, so maybe I should remind what Fredholm is. No, it's okay. Yes, I should remind. So definition: D between A and B. This these are A and B Banach. Spaces is Fredholm if kernel of D and co-kernel of D are finite dimensional. And such an Fredholm operator, for this kind of operator, one define an index which is the dimension of the kernel minus the dimension of the co-kernel. So things get a little bit complicated because we need this Fredholm property here, and moreover, we need to work with Banach spaces, and the spaces I've given are not Banach. So we have to modify. Some question? Some question? No? So we need to modify our spaces too. Now, this is how we do it. So this space C infinite xy, we will modify it by taking a Sobolev type space xy, which is formed by the exponential uy, where u is in C infinity xy, and y is Sobolev vector field, meaning that y is in LP, and dy, ds, dy, dt are in LP as distributions. Okay, and so this is can be shown to be a Banach manifold. So we have, as I said, to work with Banach manifold in order to have this Fredholm proper, to have a chance to have this Fredholm property. And so this is the replacement of C infinity xy, the replacement of the space E is LP xy, which are, I will put it like this, vector fields LP. So let me just write the fiber. EU are tangent vector field so 2W along U, which are P integrable. So you have therefore this operator, the Floer operator, now goes from this W1P xy to LP xy. So this is the framework we will work with. Now, some important thing to emphasize here is that we have to take here P. So have to take P greater strictly than 2 for 2 reasons. The first reason is that in this case, double 1P is so these functions are all continuous, and of course, I mean for technical reasons, it's more convenient to work with continuous function, namely for instance for the boundary condition, but for plenty of other reasons. But there is another point which is even more important, which is the following: if f u is, I will call this elliptic regularity. So if u is in this space xy and fu is equal to 0 or belongs to the 0 section. So this is if we have a solution which is in this space w1pxy, then this solution is smooth. Because of course we need that. We enlarge our space. So we have to, when we get these solutions, we want to get exactly the smooth solution we want it to. We don't want to get extra solutions which are not smooth, of course. So this is very important. And actually, I thought for some time when I began to think about the subject, that this a weak continuous solution of the Floer equation should be C infinity. But now I cannot prove this. So I think I really think that this is when one should start to. I mean, you do not use the W1P just for the inclusion into the continuous function. You really need it to have this argument of elliptic regularity for Floer solution. Now, well, with this setup done here, now there are the relevant theorems for this transversality problem. The first one is that for any, I forgot to say that this space of perturbation is not Banach either. So one has to modify it in order to have some Banach space, which I won't talk about that, but you have to do something because it's not Banach either. So you cannot work with in this framework either. So theorem 1, which is called Fredholm property. So this I can denote this by L P U star TW. The LP vector fields which are the vector field tangent along U to W. So for any age into U, and for any U in MX A, so any U such that FHU is equal to 0, this LU, which was the projection, which I wanted to be surjective, Remember, I want to be surjective in order to have this the property that mxy is a manifold. So this Lu is at least Fredholm of index mu x minus mu y. So yeah, this is a hard theorem one has to prove in order, of course, to get at the end of the day this the Fredholm property for this pi. Okay. Now the second one is the one which was in my plan, meaning this is a Banach manifold. So this, remember I wrote this on the board. This meant that this application y hy Luy plus gradient of h is surjective. Now this is not obvious either. I would even say that this is this problem is at the very core of this this theorem is at the very core of the transversality. Even if we added a huge space of parameters, this is a difficult theorem to prove. Okay, and we need to do it this Fredholm property. And finally, we have this property pi zx yj in U is Fredholm. So yeah, this one is not hard. This one is not hard. If you look at the tangent space here, the tangent space in HU of Z, it's exactly the couples H Y such that according to this just the kernel of this differential, of course, right? So if you take just the kernel of d h u pi, this kernel, so here you have the projection, so h is 0, so this kernel is exactly the 0 and the kernel of Lu. So of course it's a finite dimension. Okay, and the image of d h u pi, you can show it that is just it has a relation with the image of Lu. It's exactly given by this relation where psi is the application H. So this is in U and this is in LP. So again, this enables one to prove that the co-kernel is of finite dimension. Of course, here you have to compute some indices, and actually you get what you want to. So the index of pi is exactly the one which you want it to do, mu x minus mu y. So I mean, with this huge modifications, my naive plan can be accomplished. Okay, and this is all I wanted to say about the transversality. We call, so actually, yeah. One can also say that H is a regular value of pi if and only if LU is surjective, actually. And this H is for which all the LU are surjective are called, this H is called regular. So we will work from now on with regular Hamiltonians for each, so we have this transversality achieved, and so for which these spaces of trajectories are manifolds of the dimension we wanted to. Okay? Any questions? No? Yeah? Yeah, so I mean, this index comes, of course, from the computation you have to do here. So at some point you have to compute. So it's not an easy computation to do. I mean, you find the details in our book. Of course, you compute it by hand once you know once you know the. So you have to put this operator in some form, which is du dt plus J0, du dt plus S. Sorry, this is like this. So LUY via some transversality is given by this form. And then once you know that it is Fredholm, you can vary this operator among Fredholm operators. When you vary an operator among Fredholm operators, its index does not change. So what you do is you try to vary this S here in order to get a simple matrix for which you can compute. And then once you've done that, you do this computation and you compute the index. So this is the, yeah. And then the index of the other one is of course related to the index of this one. Other questions? So now this modulo many things which I left unproved, of course, because one cannot do this in such a small amount of time. Let's consider that the transversality is achieved and go further to the property of compactness. So the first thing to do when one talks about this compactness is to define the energy. So the energy for some solutions U. Let me write these two equations. So T du ds plus J du dt plus gradient UH is equal to 0. This is the Floer's equation, and the Cauchy-Riemann equation will show up. So I write it again. This is the second one. For a solution of 1 or 2, we define the energy by the formula energy of U is the integral R01 of the norm, the square norm. And some easy remarks about this. So the first remark, of course, is that if the energy is 0, then U is a constant trajectory. So U is a critical point of for U satisfying 1. It doesn't depend on S. So it's a constant trajectory. It's a critical point. The second remark is that if you, so the energy of U is, so write it like this, R01 du ds du ds. So this is the scalar product on the manifold. And now if you consider the scalar product on the space of on the space omega of paths, you can write this like minus gradient of A du ds. So this is the scalar product on omega. Say G omega, and this is not on R. This is on R only, right? So actually, this means that minus gradient, right? So this is equal to integral on R minus dA du ds, which means that if U is in mxy, so if U has some limits, and in minus infinity, in plus infinity, then the energy of U is ax minus ay. So the energy is finite. Okay. And another remark, so this was the first one, the second one, the third one, is that if U satisfies the second equation, then you can write again the energy is the integral du ds du ds. So this is the integral of omega du ds j du dt ds. Sorry, remember that this was the relation of compatibility between omega and the scalar product. And this is exactly the integral of u star omega, because this one is du dt. So this is a symplectic area. So the symplectic area of this means that the symplectic area of a holomorphic curve equals its energy. So in particular, this is positive, and this will be very important in the sequel. Now define, so the compactness has two parts, and the first important part is called Gromov compactness. Now, now what about Gromov compactness? Define M, this is the space of solution the first equation with the first equation, the Floer equation, with finite energy. And the theorem is that M is compact with in this topology. With the hypothesis, remember, I put some very strong hypothesis here. This should be taken here into account. Now, in the remaining part of this lecture, I will try to prove this theorem. Now there are many things to be said about before going to the proof. The first one is, I call this compact image, meaning that if U is in M, then there is some compact which depends on U, such that the image of U is in K. Of course, if the manifold is compact, closed, it's obvious. But since I want to work sometimes with exact Lagrangian manifolds, exact Lagrangian manifolds live in a non-compact symplectic manifold, so I have to say something. So this is a consequence of a property of holomorphic curves, which is called monotonicity. So actually, this gives an inequality between the square diameter of the image of U and the energy. Meaning that if the energy is finite, the diameter is finite, and of course, image of U intersect a compact set. So therefore, it remains in the compact. Now, what is this property of monotonicity? It says that if you have this some holomorphic strip, say U, which intersects a ball in its center, a ball of radius R, then the symplectic area of this intersection is greater than C R squared for a uniform constant C. And this, if you have, so if your diameter is arbitrarily large, then of course you exceed the energy here, which is the symplectic area, by putting disjoint balls, intersecting this holomorphic curve with disjoint balls, and then for each one we have an amount of symplectic area. So you have an amount of energy. So at some point you exceed this. So you use this to bound this number of balls. You can do this. You can put there with the energy, right? Okay. Of course, our solutions are here not holomorphic, but Floer solutions. So in order to do this properly, you probably have to go back to the other side of what I told you yesterday. So go back to the holomorphic strips. But of course, holomorphic strips and the Floer solutions are in one-to-one relation. So you can do this for holomorphic. I think you can do it by Floer directly. But anyway. So this is the first thing to do. The second one is you need a uniform bound on the energy. Now, how do you do this uniform bound on the energy? This comes from the following proposition. If U is in M, then the limit of A of US for S minus infinity and for S plus infinity is are critical values of A. Okay? I don't know anything about the limit of U itself. Okay? But I can prove something about the limit of A of US, and I proved that this is a critical value, which means that, remember that in this case, I put a remark on the board. This means consequence, this EU will be smaller than the maximum of AX minus AY for X, Y critical. Okay? And this means also that this compact set here, where is it? The compact set does not depend on U, actually. Okay? But in fact, I had to start with this one depending on U because this compact depending on U is needed in the proof here. Okay? So yeah, I probably skip this proof and give it at the end if I have enough time, which I'm not very sure, but yeah, probably. At least, not give the proof because it's long, but maybe give an idea. Now, these are the two first remarks. The third one is a particular case. So this is the case where of Gromov theorem. If there is some M such that, so let UN be a sequence in M. If there is some M's UK. If there is some M such that the gradient of UK in norm is uniformly bounded by this constant M, then the compactness is quite easy, because in this case, this means that UK are equicontinuous, and by the previous property, their image is contained in this compact set, and therefore one can apply this Ascoli theorem, saying that UN tends to some U modulo subsequence in the topology C0 lock. And afterwards, of course, you are not done here, so you have to apply again elliptic regularity. To get that actually U is C infinity and solutions of Floer. Here again, the elliptic regularity is not a consequence of the fact that the U, it's not a direct consequence of the fact that U is only continuous. You have at some point to use this property to obtain it. As I said once, it's not enough to work with continuous solution. You have to know more in order to get smoothness, right? And the hypothesis which is needed here is this one. Now, let me go to the proof. The general case. So the general case, the idea is if we are not in the hypothesis 3, then you get a contradiction. Okay? So not being in the hypothesis 3 is there is some sk tk in R times 0, 1 such that Rk, which is the norm of the gradient of uk in sk tk, goes to plus infinity. Okay? So starting from here, I will prove that we get a contradiction, and this means that we can apply this 3 to get the compactness of the space M. Now, how to proceed? We need here, so we need, actually, there are two cases. The first one is when Rk times the distance between sk tk and the boundary of R times 0, 1 goes to plus infinity. Which means that, so this is the, I work here in the, I should have told this before. I also work in the relative case. Of course, the absolute case is easier case, say, of the relative one. So I work with the boundary case. When there are no boundary, of course, it's a particular case of this one, right? So this means that this point here where the gradient goes to plus infinity is somehow far enough from the boundary, right? So what to do in this case? So take epsilon k going through 0 such that epsilon k Rk goes to plus infinity still, and actually I want epsilon k to be less than 1/3 of this distance. And now you should apply the very beautiful abstract lemma, which is called the half maximum lemma. So this lemma stays like this. Take X, Banach space, say, a complete metric space. And so take X0, X0 in X, F from X to R, F of X0, so continuous. F of X0 is strictly positive. Maybe, yeah, put here R plus. And the epsilon 0 greater than 0. Then there is some X star in X, and epsilon star, X star in the ball X0 to epsilon 0, and epsilon star greater than 0, such that epsilon star f x star is greater than epsilon 0 fx0, and this f epsilon star is a half maximum on this ball. So this means for any x in b x star epsilon star, fx is less or equal 2 times f x star. So this is a very beautiful abstract lemma, not very hard to prove. Actually, I even can do this. So let me give you a proof, because it's beautiful. So so start with the x star, try this one. So if it doesn't work, so if not, there is some x1 in b x0 epsilon 0 such that f of x1 is greater than 2f of x0. Okay, so this just contradicts the property of the half maximum. So then you put epsilon 1 equal to epsilon 0 and 2, and what you find out is that epsilon 1 f x1 is greater than epsilon 0 f x0 because of this relation. And then you try this one. And then again, if it doesn't work, if not, you have an fx2 which is greater than 2fx1, and then you put epsilon 2, epsilon 1 over 2, and so on. And so you get a sequence which has the property fxn greater than equal to 2 power of n fx0. And in the same time, because at each step you divide it by 2 the radius, this sequence is Cauchy. And this, of course, gives you a contradiction. Which means that after a finite number of steps, this sequence here is good with respect to the properties you want it to. Okay? Now, it's okay, any questions? Now, what you do, you use this half maximum lemma here in order to suppose that your SKTK is a half maximum on this. So you change SKTK and epsilon k accordingly to this lemma. You do not lose this property because of this inequality. Because of this inequality. So you just change the epsilon k with the epsilon k star and the SKTK with the SKTK star, right? So you do not lose this property. So what you get, which means we may suppose that SKTK is a half maximum for the gradient UK on this ball. Okay? And this condition here tells you that you have enough space here to put your disk given by your ball given by the half maximum lemma. right? So the half, in the half maximum lemma, you have this limitation, right? Okay. And now, once you did that, you do what is called the rescaling. So the rescaling is to define Vk of St is equal to Uk of St divided by Rk plus Sk dk. So you changed, you rescaled your sequence Uk, and then you look at the property of Vk. So Vk here, you define it on the ball of center and in the origin of radius epsilon k Rk. So that here this expression is in the disk of radius epsilon k, right? And then what are the properties of Vk? So the first property is that when the norm, by definition, the norm of the gradient in 0 of Vk is exactly 1 over Rk times Rk, okay? And it is 1. So Vk is not constant. The second property is given by the half maximum property. So when you compute this gradient St Vk, now again you get 1 over Rk, and then the gradient of Uk in this small ball here, which is where? In this small ball here. But here, our SKTK is a half maximum, right? So Rk is a half maximum. So this enables you to find that this is so this is the second property. The third property tells you something about the image. So the image of Vk is, of course, contained in the image of Uk. And this is contained in some fixed compact set K. Okay? And the final property is that when you look at the equation which satisfies this Vk, it's the following: dvk ds plus j dvk dt plus 1 over Rk gradient of h in Vk is equal to 0. Now, this one and this one enables one to apply Ascoli's theorem and to get that Vk converges C0 to some V. Okay? And this V is defined, since this goes to infinity, it is defined on R2. Okay? And then elliptic regularity implies that this V is C infinity, actually, and the convergence is C infinity. And afterwards, you go here. And here, what you see is that when K goes to infinity, actually this V is holomorphic. Okay? And then 1 tells you that V is not constant. Okay? So you got this, you got this V And what can you do with is the following thing. You need this property. Now remember, the image of V is part of the image of VK is part of the image of UK. Okay, so it's not surprising that the symplectic area of VK is less than the symplectic area of UK. And the symplectic area of UK is bounded, right? So what you can we have a uniform bound on the energy. Remember, okay? You had a uniform bound on the energy. So all these UK have uniformly bounded energy. So all these VK have uniformly bounded energy. So this means that the energy of V is finite. And to end this argument, you need the theorem of removal singularity. V R2 in W holomorphic and of finite energy, then V can be extended holomorphically, but actually I only need smoothly to the sphere. Okay. So this is the object which will provide a contradiction. This is actually a holomorphic sphere. So the contradiction is the following. This non-constant. So a non-constant holomorphic sphere has positive energy, right? But this is the energy, as I said, is the symplectic area. Okay? And this, with pi 2 of W equal to 0, must be 0. Because of Stokes. Okay? So this is a contradiction. So yeah, holomorphic spheres are obstruction to the compactness of these spaces of trajectory. And this condition here is made to ban holomorphic spheres. Now let me draw you a picture because it's not very, probably not very intuitive. So what happened here is the following thing. So we had this, at the source we have this R times 0, 1. And here is our manifold W, in which we had this Lagrangian L, and the UK are Floer strips like this one. And here we had this small ball where the gradient goes to infinity. Now we rescaled. This is the ball epsilon k RK. So this was rescaling. So as a composition, we got this VK. Now this VK, this ball here, and the VK, so goes like this, forms here on a surface a sphere, which at the limit becomes holomorphic. So just like you blow into this point where the gradient explodes at the in the image, and what you get is this holomorphic sphere growing on this Floer strip. Okay, so you need something to prevent the occurrence of this kind of spheres. Now, I still have 10 minutes.
Why this blow up doesn't happen on the bottom?
I'll become so. Remember, I put as hypothesis the fact that as supposition the fact that this point where the gradients go to infinity was far enough from the boundary. Okay, so now let me remove this hypothesis. So this hypothesis was RK distance go to plus infinity. Okay? Distance from the SKTK to the boundary. Let me actually suppose that this distance is TK. Okay? So I mean this point is closer from this. So here you have TK, here you have 1 minus TK. So let me suppose that the distance is this one. Okay? Now this was the first case. The second case is the contrary. So RK TK goes to some other limit, finite. Okay. Now what happens in this case? In this case, what you can do is you cannot have when you do this. When you take epsilon k such that, as before, RK epsilon k goes to plus infinity. Now, if you take some epsilon k like that, what the main how to say difference is that you cannot have a whole ball inside. Okay. So we have this kind of ball, SK TK of radius epsilon k, which intersects with t greater than 0, of course. If not, you cannot put it into it. Okay? And so what you do is you apply the half maximum lemma on this kind of ball, on this kind of on B prime. Okay, so you replace this how to say this cut ball with another one in which this point is a point of half maximum. And now you do the same thing to see what it happens. So put Vk of St. So I say, yeah, so we suppose now that this point is a point of half maximum on this how to say incomplete disk, right? And put Vk as before, Uk St Rk plus Sk Tk. Now this is defined on this ball. But intersected, you need to have this here, you need to have T positive, right? So T greater than minus Tk Rk. Okay? So you do exactly the same thing. So you have this Vk with all these properties, but in the end, what you get is something which is not defined on R2, but something which is defined on, so same same procedure, gives you a V which is defined on R2 intersect with T greater or equal than minus D star. Okay? So this actually, another important things to say here, that if you have V S and minus D star, okay? So this is defined on this kind of space. Okay? It's holomorphic. It's like the other one, except for the fact that it's not defined on R2. It's defined on a half plane. Now this Vs of minus D star is the limit of Vk of S and minus Tk Rk. Okay? And then if you replace here, you find that it's the limit of Vk S on Rk plus Sk. And then if you replace here T by minus Tk Rk, you get 0. Which means that the image of this boundary here, this is UK. UK sends this 0 into the Lagrangian. Okay? So what you get here is a half plane with a Lagrangian boundary. So this half plane you can consider that it as being R times R plus, and then its conformal equivalent with the disk it's holomorphically conformally equivalent with the disk without -1, and then what you do here is the analog proposition is that if EV, this was the theorem of removal singularity. So saying that if the energy is finite, then you can extend V extends to D2. Now let me now draw you a picture. Which is the analog of this one, right? Just to show you what it happens, maybe here. Now, so we started with this kind of picture, going to the holomorphic strip lying, holomorphic strip lying on L, right? And here we have this, incomplete ball. I don't know how to say, right? So we rescaled, and we found the ball here. This is T greater than minus Tk Rk, and this is the ball B0 epsilon k Rk. And actually, I should use a different color from this one. Now, what happened here? What we see is that this part here, so let me draw it like this. So this part here goes into the Lagrangian, So we have this part here which goes like this. It gets bigger and bigger. This one. Okay? This part here, the blue one, gets smaller and smaller. Right? Okay? And above this appears this image of V like a disk becoming at the limit this blue part becomes a point, and this disk becomes a holomorphic disk with Lagrangian boundary. Okay? So this is what happens when the point where the gradient goes to infinity is very close to the boundary. Okay? So now I will finish with this remark. So what we do to get a contradiction here, again, we use this condition. Which is good to ban holomorphic disk. We use it like this. So again, 0, we have a disk non-constant of positive energy. So this is the same as the symplectic area. But because of this condition, pi 2w WL equal to 0, this integral is the same that the integral on the disk lying on the Lagrangian. And on the Lagrangian, omega is 0. Okay? So this condition plus L Lagrangian implies that this is 0. So we get a contradiction. Okay? So yeah, finally what one should say is that this important property for the compactness which is a part of so the compactness is a part of the story of any Morse type theory. In this case, a very important preliminary step is this Gromov compactness. And in order to have Gromov compactness, there are two phenomena you have to avoid. The one is the occurrence of the bubbling. I didn't write about bubbling sphere and bubbling disk. These are the two phenomena one has to avoid. And of course, I put here the right condition to avoid them. Okay, so it's bubbling is like just like a, if you imagine this like a film of soap, you just blow here, bubbling and you just blow here at this point, and you get a disk on the holomorphic disk with boundary on the surface. I'm finished. Thank you.